I would like to introduce myself. I am Vicky Quad from ARK Infosolutions, and I am taking care of the low frequency part of the Ansys solution. So whatever the solutions we offered offered by the Ansys regarding the electrical department, or you can say the low frequency division, and then like the whatever the electrical appliances you want to build, like transformer. So for this webinar, this is a transformer webinar. Inductors are there, actuators are there. So there are multiple applications are there regarding the electrical point of view. So each and every applications you can simulate by using the Ansys tools. So for the different tool for the different applications we have a different tools. Okay, suppose for the motors we have a motor CAD tool is there. So that I will explain in the upcoming slides, like which tools is preferred for the which type of simulation. Okay, first so this is basically the Ansys product portfolio. Okay, so whatever the Ansys offers, okay, in which departments, in which academics department the Ansys will be helpful. So for today's point of view, it is a just a second. So in the electronic segment, okay, so in the electronic segment, you can see the multiple tools are there. So each tool has its own speciality. Okay, so for that speciality the tool is going to use. So in the electronics, the electronics department is divided into two domains. Yes sir, any issue? Okay, so electronic segment is divided into the two parts, like low frequency part and the high frequency part. So for the low frequency part, the tools are there, which is the iSpec is there, Maxwell, Concept TV, MotorCAD. So these are the four main tools are there for the low frequency domains, and the other tools which you can see here for the high frequency, like HFSS is there for the antenna design, then SIO is there, Charge Plus is there. So these are the multiple tools for the high frequency, such that the structural tools are there, which use for the structural reliability to check the structural reliability of the any transformer applications or inductor application. After doing the thermal analysis, then the for the fluid or thermal analysis, we have a fluid tools are there. So there are multiple tools are there, and one tool is there which is called the Ansys Twin Builder, which is basically used for the system simulation tool. As a system simulator, we can use the digital twin. The tool name is called the digital twin is the concept, and the tool included in the Ansys, which is called as the Ansys Twin Builder. And then rather than this physics, we have autonomous vehicle simulations, embedded softwares, and like that the now you know, like ChatGPT is the trending part, like the AI is there. So Ansys introduced its AI also, like whatever the questions you have regarding the any simulation part of the Ansys, so you can directly ask the Ansys ChatGPT. So it will give you the answer, like it will give you the answer. Otherwise, if it's not give the answer, it will provide you the material, like this is the material for that specific part, so you can refer to those parts or refer that material, so you will get the better solution. Okay, then for the design, the 3D discovery is there, and for the optical simulations, we have optical tools are there. For the mission engineering, satellite communication part, that takes care of the SDK part, and then the cloud is there also. So like this software is based on the cloud also, Ansys cloud, you can operate it on the software base also. So this is the two ways to use the software, Ansys software. And these are the some world-class companies which basically leverage the Ansys platform for their research and development. It includes the aerospace, defense, energy sectors. All the uh, world-class companies are there that you can see there. Along with these companies, the academic clients are there also. Okay, so inside the India, whatever the clients you can see that the various IITs are there, NITs. So they are basically use the ANSYS software for their research and development, for their research part. Okay, so mostly the PG and the PhD scholars are there. So they are mostly used for the research purpose, and whichever the students are there in their BTech, so they can use this software So they will get more familiar with the software before uh, take part in the industry application. So now we'll start our main discussions on the transformer part. So this is basically the products that we include in the Ansys low frequency part. So one is the Maxwell is there for the, it includes the 2D and 3D electromagnetic solvers. Okay, both magnetic and electric solvers are there, and whichever the applications you have regarding the electrical point of view, so you can simulate this under the Maxwell part. And then the MotorCAD tool is there for the specialist in motor technology only. Okay, then the Simplorer part is there. Simplorer is basically the twin builder, which has the capability to do the system simulations or the circuit level simulation. Then the iSpec is there for the thermal part. Okay, like Maxwell taking care of the electromagnetic part. So after the electromagnetic simulations, the losses are there, the EM losses are there. Now you want to transfer those losses in the any thermal solver to get the like the thermal parameter, how much the heat flux is there, how much the temperature at this part. So if you want to see the thermal result, so you have to transfer your Maxwell results in any of the thermal solver, like iSpec is there or the Fluent is there. So you can use any of the solver to get the thermal results. Then these are the applications are there, like you can see the applications that we mostly covered in the Ansys low frequency segment. This is the electric machines are there and drives, the transformer and inductors. You can design it in the Maxwell. Then the actuators are there, sensors are there. Here the one sensor example is there. This is the Hall sensor example. Wireless power transfer or wireless charging application. So now this is the trending part for the EVs are the wireless power transfer. Then the induction heating, bus bars and cables, and electrification. So like powertrain design, motor design, circuit design, inverter design, converter design. So all these parts you can do under the Ansys Maxwell and the Ansys simpler part. So these are the tools are there, and these are the applications. That applications basically covered inside the tools that we saw in the last slide. These are the tools are there, and these are the applications we covered in those tools. By using those tools, we can do the simulations and see the results and validate our results with the experimental one. Now we'll go to the our main focus point is the transformer one. Okay, so first we will see the transformer designs, how the transformer is going to design. Okay, then the which of the capabilities are there for the transformer in the Ansys, what Ansys capabilities has and what Ansys offers for the transformer simulation. Then we see some case studies and the success stories, and then the summary part is there. Okay, so now the basic discussion about transformer is like, for the transformer it is divided into mainly the two categories. Okay, for the FEA simulations that you can see here, FEA simulation, which is the mechanical finite element simulation method is there. Okay, finite element analysis. So the two categories which are the electronic transformers and other one is the power transformer is there. So electronic transformer is like our mid power range is there, something from milliwatt to, this is the power range you can see there, from milliwatt to some watt is there, is the power range for the electronics one. And if you want the higher power range, then we have to use the power transformer. So it is based upon the frequency also, like how much the switching frequency you have on the basis of a transformer. So this is basically on that also. But the main difference between the electronic transformer and the power transformer during the simulation. Okay, so in the electronic transformer you doesn't need to simulate that much of the electric field effect. Okay, uh, you can cover most of the details or the most of the part by using the magnetic simulation only. Okay, if your uh, supply current is like the AC current or the non-sinusoidal is there. If the sinusoidal is there, you have to use the AC current solver. If you have the non-sinusoidal, then you have to use the transient one solver you have to use. But in case of power transformers, you have to use the AC current solver as well as the electrostatic solver. okay, to get the electric field effect, because the effect is there in the power transformer is much more rather than the electronic transformer for the electric field. So you have to simulate both the fields here for the power transformers, the magnetic field as well as the electric field. So for that the different solvers you have to use here. Okay, like you can see here mention the ED current solver primarily used for the sinusoidal excitations, but if you have the non-sinusoidal excitations you have to use the transient solver. And in the power transformer you can see that the ED current solver, this is the magnetic solver, okay, and then the electrostatic solver is there, so it's the electric field solver. Okay, so you have to give the excitation parameters like voltage or charge, so it will give you the electric field effect, how the electric field effect manipulate your transformer designs or changes your design parameters or the output parameters, that gives you the idea. And in these simulations you can use the linear as well as the non-linear materials. Both the materials are available in the Ansys library, so whatever the material you have you can use those materials. Otherwise if you have your own materials that you design specially for your transformer design, so you can implement those materials also by creating your own material inside the Ansys library. Okay, uh, then this is the methodology is there. So there are the four methods are there in the Ansys to create the transformer design. Okay, so the four method, the first method is like a ETK method is there. Okay, so ETK is basically the electronic transformer ACT extension is there. So now the question is, what is that ACT extension is there? Okay, so ACT extension is like a ready-made tools are there. Okay, the ready-made toolkit is there for the transformer only. So you have to just give the parameters like which type of core you have. Okay, like E type core you have, so you have to select the core type, you have to select the supplier type. Okay, and you just need to give the dimension parameter. Then you have to select the winding layers, how much the layers you have, which are combining the series or parallel electrically, that you have to give. So these are the some parameters regarding the transformer you have to give, and it will create the design, it will create the Maxwell design for you. Okay, with the circuit is there, okay, the excitation circuit. Then the result parameters are there, some result parameter they are giving. Okay, so it is automatically the design is created, it doesn't need to do anything, you have to just create the circuit, create the transformer design by using the ACT extension, and then you can directly simulate this design in the Maxwell 3D or Maxwell. Now the PMAG the tool is there, so which is the more basic tool is there for the transformer design. So any type of transformer you can design by using the PMAG, but with the PMAG is like a more basic tools, you have to give the more manual effort rather than the ACT extension. Okay, to use the PMAG for the transformer design. Then the one simple method is there, the CAD method is there. Okay, so CAD is basically you have to design your CAD model for the transformer. Suppose this is your planar transformer, you can see in the image. Okay, so these planar transformers you have to design itself in the Maxwell. Okay, or you can design it in the any of the CAD software and you can import that design in the Maxwell. So both way you can do the CAD model like itself in the Maxwell, so you can build it, or you can import it from the other CAD softwares and you can just uh, import that software in the import that model in the Maxwell. Then the Q3D, this is for the bus bars applications. The Q3D tool is there for the to calculate the parasitic parameters. Okay, now these are the four ways to create the transformer. Now all the designs you can see, the ACT extension itself create the Maxwell 3D design, PMAG also create the Maxwell 3D design. So Maxwell 3D is the main tool, the advanced tool for the transformer analysis. So whatever the itself in the Maxwell 3D, it includes the electric field and magnetic field solvers. You have to pick the solvers. Like if you have to solve the AC sinusoidal, then you have to select the AC current solver. If you have the non-sinusoidal, okay, non-sinusoidal AC is there, then you have to pick the transient solver is there. and it has some system analysis capability is there also, which is the simpler tool is there. So we called it as a twin builder also. Okay, that capability wise it is different, the simpler and the twin builder, but for the system level analysis the mostly twin builder capability is getting. Yes, and then the optimetric setup is there also. The optimetric setup is for the parameterization, okay, to optimize your design. So if you have any parameters, you can just parameterize it. Okay, you can just assign the variables and it will, and then you can simulate the same design for the different parameters. So you will get the one optimum results at the optimum combination is there, then you can find it. And after the electromagnetic analysis, so after this we'll do only the electromagnetic analysis. Now we have to do the calculations of the thermal also. Okay, so the two types of thermal calculations are there. Only the thermals are there which doesn't include any fluid. Okay, so if the fluid is not included, you can just directly transfer to the Ansys mechanical to calculate the thermal parameters. Okay, so only the conduction parameter is included here in the Ansys mechanical thermal. Then if we have the fluid also, okay, so any flow parameter is there in your model, so you can transfer it to the iSpec ADT. So you have to select the thermal with flow. The both the capability it has in the iSpec, like you have to select it, like the flow is involved in your simulations or not. Okay, or the only the mechanical part is there, only the conduction part is getting involved there. So we have to see that. Now here you can, these are the model designs parameter and these are the field solution. Okay, these are the two-way solutions you can see. The two-way coupling part is there. Okay, so any of the results you transfer from Maxwell to mechanical. So if you after the coupling, after transferring the results into the mechanical or the iSpec, if you change any parameter in the Maxwell 3D, your losses is getting changed. So the same losses is getting changed in the mechanical window also or in the iSpec window, and it will give the results on the changing parameter, not for the old parameter. So whatever the change is there here in the Maxwell's, so the same change will happen in the mechanical thermal or in the iSpec. But when you did the two-way coupling, then the transformer methodology is there. So like in the Ansys Maxwell is there. Okay, so Ansys Maxwell has the 2D 3D magnetic finite element analysis involved is there. It has the both DC and the frequency domain solvers are there. Okay, means it has the both DC current solver and the AC current solver is there. Then the optimization parameters are there, and one HPC is there. So HPC is basically the high performance computing to increase your course, to leverage the more course, to increase your simulation time. Okay, to increase your simulation time means to reduce the simulation time. Okay, to get the results in a much faster way. Okay, and then the Ansys multiphysics is there. Okay, the two-way coupled. Then the simpler tool is there, you can call it as a twin builder also for the electrical circuit analysis. And one of the key advantage of Maxwell is like the automatic adaptive meshing technique is there. So like in the previous slides we saw, it uses the finite element method. Okay, the FEM method to solve the equation. So to solve the FEM method, to do the calculations with the help of FEM method, you have to mesh the geometry. Okay, you need to do the meshing on the geometry part, but in the Maxwell's you doesn't need to do the meshing part. So for the magnetostatic solvers, whenever you are using the DC current solver or the AC current solver, sinusoidal, okay, sinusoidal AC current solver, that time you doesn't need to worry about the mesh parameter. The only time you have to give the mesh parameter is when you are using for the transient simulation. Okay, but in the transient simulation also you have to give the 2-3 parameters only. It is very simple to give those parameters. Okay, so it will automatically doing the mesh. Okay, the number of passes are there, it will automatically, you can see here, this is the last adaptive pass. Okay, so where the area is more concerned area about the flux or any quantity. In that part the mesh elements are more. You can see the fine elements are there at those particular parts, like that at the corner parts you can see here. At this part the more fine elements are there, so you will get the more fine elements. If the more fine elements are there, more chances of getting the better accuracy. Okay, so if your mesh is too fine, then you will get the most of the accuracy, means the better accuracy you can say. And this is the ACT extension is there. Okay, here the parameters you have to give. You have to select the model unit, supplier, the core type you have to select. Okay, this type of designs. Then you have to give the winding parameters, the number of layers. Number of layers is like a number of windings are there, primary and secondary. If you have the, then you can give the, if the number of the windings are two windings are there, so you can give the number of layers too, so it will create the primary and the secondary one. And the electrothermal ACT extension is also there. This is the coupling part, to couple the electromagnetic, like the Maxwell part with the iSpec. The one ACT extension is also there. This one is the ACT extension and the name is electrothermal. And the PE expert is there. So this type of design, this is the buck converter design that you can see there. Okay, and this type of analysis you can do inside the Maxwells. But before the Maxwells, you have to create the, you have to give the more time to create the transformer design by using the PE expert. And these are the some of the CAD tools. Files supports are there that supports the Maxwell 3D itself. Include the various files are there, like SolidWorks, CATIA files are there, STL files are there, step files are there, IGS files are there. So DXF files, if you have the 2D file, 2D AutoCAD file, that 2D AutoCAD files also supports the Maxwell 3D. So whatever the files you have, whatever the CAD files you have, either it is 2D or 3D, so it is supported to the Maxwell part. So if the 2D file is there, you can import into the Maxwell 2D. If your file is 3D, you can import it into the Maxwell 3D. The same part is there, the same license part is there. And now the Maxwell part. So what is the capability of Maxwell's and what it includes inside the Maxwell? So now you can see Maxwell itself includes the 2D and 3D electromagnetic field problem using the finite element analysis method. Then it has the 5 solution types: electrostatic, magnetostatic, these are the static ones; ED current, they are the AC current, sinusoidal form; this is the transient electric, the transient electric solver, and the transient magnetic solver is there. Okay, and what are the outputs that you can get after the analysis? Like RLC parameters, you will get forces, torque, losses includes the winding losses are there, core losses, okay, the stray losses. So you can expect those losses. In the simulations of this type of applications, you can simulate it. Then the iSpec is there for the thermal part. Okay, you have to do the two-way coupling with the Maxwell and you have to enable like steady state thermal is there or the transient thermal is there, the conduction point is there or the convection. If the flow is there, if the air is involved, if the any fluid is involved there, so the 100% chance of getting convection is there. That means the convection point is there. Okay, so if the air is not involved or fluid is not involved, then only the conduction part is doing, and for that conduction part only the results will be given. And then the mechanical part is there for the structural analysis or the reliability purpose. And then the Ansys CFD is for the flow simulation. So you can use either iSpec also for the flow simulations or the thermal part, or you can use the Ansys Fluent. So both the tools are there. So Ansys Fluent is basically the advanced solver for the CFD analysis, specifically the CFD analysis solver. Then we have the Simplora tool is there, which includes the circuit analysis part of there itself, it has the component libraries. You have to just drag and drop the components, whatever the component. Like here, this is the circuit, you can see. You just need to, here the one library is there, you just need to drag and drop the component. Suppose you want the register, you just need to like drag and drop the components here and connect the multiple components with by using the wires, and give the ground connections and the source connections, and you will get the results for this circuit. So it is as simple as that to create the circuit and see the output parameters for the each circuit components that you use in your simulation. Now the specific advantages for the electronic transformer is like it has the 2D and 3D frequency and time domain solvers are there. Both the frequency, the AC current solver is your frequency domain solver, and the transient is your time domain solvers are there. Okay, it has the adaptive meshing technology. Okay, then it supports the HPC to reduce your simulation time if your model is too complex or if your model is too big to simulate. Okay, then it has the two-way multiphysics coupling. Okay, the two-way multiphysics coupling means it is the magnetic, the thermal part, okay, and the magnetic and the mechanical part. So you can simulate, you can transfer those results easily by using the Ansys tools for the multiphysics part of your transformer. Okay, like if you are designing the transformers, you have to do the electromagnetic parameters first, then you have to proceed with the thermal and the like the reliability part also. So you must have to check those parts, like you can't skip those parts. Okay, so if you are designing any transformer, so you must need to check those thermal parameters and the reliability, the mechanical part, the stress is there, the deformation is there, that you need to check. And these are the some key features are there that you can see, that we basically see in the transformer applications whenever you are simulating the. Then the proximity effects are there, proximity effects, skin effects are there. Then the leads wire modeling technique is also there in the Maxwell's. We have to provide it in the material part. And the AC frequency effects is there, the AC frequency solver we have, adaptive frequency you have to provide. Then the winding leakage and incremental inductance, you can find out the leakage resistance, sorry, the leakage inductance is there. Then the capacitance if you are using the electrostatic solver. Then the electric field breakdown also you can simulate. Then the interconnected windings, how the unbalanced currents are there, if you can just plot the currents or just find out the current, how much the current are there at the one limb, and if your power transformer is there, so at the other limb how much the current part is there, that you can simulate and find out the if there is any unbalance or not. Then you can find out the core losses. For the core losses, the it is depend upon the basically the materials. So the materials for your core, if it is steel material or if it is any power ferrite material, so you have to select the core loss models. Basically it depends upon the temperature as well as the frequency. You can simulate your non-linear core model with the different frequency parts or the different temperatures. You just need to provide your BH curve, whatever the non-linear BH curve you have, you just need to provide that BH curve for the different frequencies and the different itself. In this point you can see here the frequency dependent, temperature dependent, and the non-linear method. It supports all these capabilities, okay, for the core loss parameter. And then the most important is the system simulations using the frequency dependent ROM techniques is there. So ROM is basically the radius order model is there. Okay, so the radius order model like it is like a 0D model, okay. So by using your parameters, if your simulation file, if your Maxwell file is too big, okay, so it will take the most of the common results are there or the most important results. Okay, so it will take the most important results. Okay, it will solve some equations, it will solve some 0D equations, calculate the most important parameters, and on the basis of those most important parameters, okay, it will calculate the further parameter. So the accuracy is also very good whenever you are using the, it is not like if you are using the ROM techniques your accuracy is getting decreased. Okay, so your accuracy is not there, your accuracy is also very high when you are using the ROM techniques. Okay, but the advantage is like you can reduce most of your simulation time. It is like about 10x to 6000x simulation times you can reduce if you are using the ROM techniques. So this is the benefit of this ROM techniques. The proximity effects in the solid windings. So the both options we have in the Maxwell. If you are simulated within the solid windings or the standard windings are there. Both options you have, you just need to, if you are selecting the solid windings, then you have to pick the number of conductors as 1, and if you are using the standard ones, you have to give the number of conductors, like whatever the number of conductors you have for your winding, you have to give like 10, 20, whatever it may be. Okay, then the these are the ohmic losses plot. You can see here, the higher the losses, uh, near the core gap regions, you can see the higher the losses are there. Okay, and at this part particularly the medium losses you can see, so you can see the losses are there, and you can see how the current distribution is there, how the flux distribution is there on the, you can, on the flux distribution point you can find out like when the saturation is happen there. Okay, if the saturation is happen at what is the saturation point is there, so all those points, all those flux plots you can see by using the Ansys Maxwell. Then the leads wire technique is there also, that I already talked. Like it had in the material sections, you have to provide the leads wire technique. Your diameter is there. Suppose your leads wire is, suppose the circular is there. Okay, so you have to provide the diameter. If your leads wire is like rectangular is there, then you have to provide the length and width sections. That two sections you have to provide. Then the most important thing is, but if you are using the leads wire techniques, you will get the losses, your losses is getting reduced basically. Okay, you can find out the DC resistance losses are there, proximity effect losses, or the skin effect losses are there. So you can find out the multiple types of losses. Okay, in a different way, like you will get the losses. And then the validation, one validation case is there for the leads wire techniques that you can see. So the inductor, we simulate the one inductor part. Okay, this is the plane, RZ is the plane, this is the 2D design. Okay, and we use the solid strands. Okay, at this particular frequency the resistance is around 11.25 milliohm, and the CPU time is taken around 3 hours. At 100 kilohertz the resistance is increased and it will goes around 228, okay, milliohm. Then we use the RZ 2D leads wire technique. Okay, so the difference is now is the your CPU time, is your computation time. Now you can see that the both simulations are same. Okay, the plane is same, the design is same. This includes the strands. Okay, and this includes the leads wire. Now you can see the simulation time, and the results are around same results at the same resistance you can find here. Like at this frequency is the 0.1 hertz, it is the not that much of difference in the resistance, and at the 100 kilohertz also that much no difference is there, but the very much big difference between your simulation time, this is the CPU time. Here the for the solid strands it takes around 3 hours, and for the leads wire technique it takes around 4 minutes only. Okay, so that is the benefits of using the leads wire technique. And now you can simulate. Why we use first 2D? Because 2D gets the results faster than your 3D. So first we have to do the 2D. Okay, then we optimize our design in the 2D sections itself, then we can proceed for the 3Ds. If our validation case if the case, now we have to validate this case, then you have to proceed for the 3D simulations case and then the validation. In the 3D also the leads wire technique, the resistance is same around, the resistance is nearly equal, and the simulation time is getting increased here. But this is for the 3D part. Okay, here you can see for the 2D solid strands it takes around 3 hours. Okay, and same leads wire, but for the 3D it takes around 2.5 hours. Okay, so the same simulations if you are doing it on the 3D now, so it will take around 10 hours time, nearly equal to 10 hours time it will take for the 3D simulations by using the solid strand. So that is the benefit of leads wire. Okay, and these are the parameters are there we use for this one: strands diameter and the skin depth. You can see this is the AC frequency effect. The current density plot is there to show your skin effect, and the proximity effects is there. Okay, these are the flux lines, and this is your current density plot. You can see, and this is the frequency dependent, including the RLC parameters are there. Then the leakage inductance calculations are there. Okay, you can find out the flux lines are there, and this is the some of the theory are there regarding the leakage inductance calculation. For the primary one the formula is different, the secondary one for the formula is different because the coupling coefficient is different. This is the inductance matrix, this is the coupling coefficient. Okay, you can see the coupling coefficient, these are the formulas are there for the leakage inductance calculation. So you can see here itself leakage from energy, from matrix, and from the CC. So in the three way it is calculating, and now you can see the difference there. Then the incremental resistance is there, inductance is there, then the winding capacitance are there. As same as the inductance, the capacitance matrix is also getting calculated here. Then this is the electric field are there, the voltage plot is there, this is the electric field plot is there based on the excitations you provide. This is the interconnected multi-winding designs are there that you can see. There are the multiple cores are there we assign. This is the design of the PE experts. So this type of designs if you create in the PE expert, so this type of design is created. The core part is there, gap is there, the bobbins are there. So there are the multiple options you have. If you want to create, you can create these models using the PE expert. So but the more manual effort is required in the PE expert. And then in the the Maxwell circuit option is there. If you want to give your excitations by using the circuit parameter, so this option is also there. Maxwell circuit is there, and this circuit is for the ED current analysis, then the other is for the transient one analysis. The same circuit is there in the Maxwell circuit. In that Maxwell circuit we have to create the circuits to give the external excitation parameters to the Maxwell design. Then the current imbalance in the parallel windings you can see. Okay, and these are the excitations we simply provide. Okay, and in the excitations you can see the various HV and LV sections are there. Okay, and itself in that section the coils are there. Okay, so these are the coils in the HV1, HV2, these are the HV coils are there, and the resistance we provide here. Here we doesn't give any values there. Okay, we give as external only, and in the circuit we provide the resistance and the inductance value. Whatever the load parameters we have, okay, we give those load parameters in the circuit section. And this is the graphs, only the graphs for this is the current density plot is there. These are the winding currents graphs that you can see here. And now the core loss computation methods are there. So the two methods are there mostly used in the Maxwell. The ferrite core loss computation method. Okay. These are the power ferrite. If your core is made up of the power ferrite material, so you just need to give this data. Okay, the core loss now model you have to select power ferrite, and you have to give the CM, X, Y. So this data you can get from the data books. Okay, okay, the material data books, you will get those values for the power ferrite material. This type of data books you can see. Then the frequency dependent properties there, you can give the frequency dependent the BH curve also. Here the BH curve looks like this one. Okay, this high flux 160, this parameter is there. You have to give the H and B values. Okay, or you can import the data set also. If you already have the data set, you can import the data set. And this is one of the temperature dependent conductivity part is there. Initial we uh, calculate the initial loss density at the particular room temperature is there around 22 degrees Celsius, and at the operating temperature the loss density is getting increased, but the frequency is same that you can see here. The same frequency is there 100 kilohertz, but as the temperature increases your conductivity decreases and your loss density is also getting increased. If your conductivity decreases, then the loss density is getting increased. This all depends on the temperature, so that's why you have to simulate the temperature part then after the electromagnetic section. And this is one of the example of Maxwell and IcePack 2D couplings. Okay, the sorry two-way coupling. Okay, the two-way coupling. This is the Maxwell part. Okay, and this is the temperature part that you can see. Okay, the both the designs are there in one project. You can simulate the different designs in the one project, solve with airflow or the natural convections. So if the natural convection is there, no airflow is there, then it is only the thermal conduction part is there. If the flow is involved, then the convection is also taking part. So that is the basic physics for the thermal. You need to uh, learn for the you need to learn the simple physics about the thermal parameters if you are go from electromagnetic section now to calculate the thermal parameters. Like you have to know, like if your temperature is in the previous slides we see, as our temperature is increases our conductivity is getting decreased, but we have to know like as the my temperature is getting increases, how much how much percent of my conductivity is getting decreased, that you need to find out. It is based upon the mostly the materials that you are using. Okay, so like if you are using any steel material is there, or the suppose copper you are using. Okay, so if your temperature is goes around the 22 degree, okay, so beyond the 22 degree your temperature is there, your the conductivity value is getting decreased by 0.37 something, 0.37% conductivity value is getting decreases as the temperature goes above the 22 degrees Celsius. So this is basically the data sheets formulas, or you can say the data sheets value we have to find out to calculate the accurate temperature part. Okay, so like at which point the conductivity is getting decreases, at which point the conductivity is getting increases, which is based upon the temperature ones. Then this is the Ansys thermal coupling is there, the same. So the previous one we saw it is in the ice pack. Now this thermal coupling is in the ADT, okay, or in the Ansys workbench is there, solid inside the Ansys workbench. Okay, here the Maxwell 3D part is there, and we transfer our results into the, like give the excitation or the input for the steady state thermal part, and it will give the temperature parameters are there. Okay, these are the winding loss parameter and these are the temperature. And by using the PEG ROM you can simulate your Maxwell model and connect your Maxwell model inside the Simplorer also. And this is one of the example of the forward converters in the Maxwell ROM. By using the Maxwell ROM, these are the Maxwell ROMs are there, this one and this one, two Maxwell models are there, and this is the converter you design in the Simplorer part, or you can say the twin builder part. Okay, so the whole model you can simulate itself. It includes the state blocks also. Okay, the multiple electrical parameters are there. Okay, so if you have any load parameters, any mechanical load is there, okay, not in these applications. Okay, so if any of the applications you have, and suppose the motor is there, so the mechanical load parameter is there. Okay, so you can add the mechanical load parameters also there in the circuit. That mechanical load parameters also there inside the twin builder library. Okay, so that I will show you which of the component parameters are there in the simpler. Okay, so once we finish this presentation part, we move for the hands-on session, like for the software demo part. Okay, and these are the conclusion is there only, like what are the capabilities are there, the ACT extension is there, then the ROM technique we basically use for the solver, like the system simulation part. Okay, then the coupling part is there between the electromagnetic and the thermal, the two types of couplings we see, and the in a two way we can couple our electromagnetic and the thermal parameter. So up to this, so for now this is the presentation is over now. Okay, so if you have any doubt regarding this presentation, so you can ask, otherwise we have to go for the software demo part. So if any participants have any questions, you can just ask the questions, or you can just type your questions in the chat box. Okay, so I will give the answer. So if anyone has any questions, you can just put in the chat box. Okay, so I will give the answer. If you don't have any questions, then we can proceed for the. Okay, so we'll just proceed for the simulation part. Okay, the software demo part. Okay, now you can see, so this is basically the software window is there. Okay, for the Ansys electronic desktop. So right now I am using the latest version, which is 25R2. Okay, and in this Ansys electronic desktop part, the electronics tools, whatever the electronics tool we have, it is included here, both the high frequency and low frequency. It is not like only the low frequency or the high frequency tools are there, both high frequency and low frequency tools are there. So it has the, like, low frequency tools, we have the iSpec is there, then the Maxwell is there, and then the Simplorer is there. Okay, now you can see in the in the Maxwells, the 5 types of tools are there. Okay, so the 5 types of tool means the Maxwell itself divided into the Maxwell 2D and 3D. If you have specifically Maxwell 2D design, okay, then you can select the Maxwell 2D. If you want to simulate any 3D design inside the Maxwell, then you can proceed for the Maxwell 3D. And now if you want to create the circuit, external circuit, then you can go for the Maxwell circuit, or the RM expert is there for the analytical motor design part. Okay, not the FEA based approach. RM expert is basically use the analytical approach, like the whatever the hand calculations we did for the motor calculations, that simply the calculations is done by the software itself, and it will give you the, like, a quick result is there within a second, within 2 or 3 seconds it will give you the results. Okay, so now I will show you one of the power transformer example is there. Okay, first I will show you the ACT extension part. Okay, how the ACT extension is going to use here. And so to for the ACT extension, this one is the ACT extension part. This type of ACT extension is there. Okay, this one you can see. Yeah, this is the ACT extension is there. It is like a toolkit is there. If you doesn't get any ACT extension part, you can just see as a toolkit is there for the transformer design. Okay, here you have to give the, like, segmentation angles. So whatever the curves you have in your model, okay, so that curves are there. So what type of angle is there? Okay, what is the angle between those curves, that you can give there. And the supplier type you have to give Philips, TDK, or Ferox cube. Okay, the most of the Ferox cubes are there. Then the core types, the multiple core types are available here. Okay, so the core type is there. Suppose the multiple core types are available here, you can see. So I am selecting, for now it is the ETD. Then the core model is there, you have to select the core model also. So I'm selecting one of the core model, this one I'm selecting 44, 22, 15. Okay, then these are the D1, D2, D3 parameters that you can see in the image itself. Okay, you have to give those parameters. Okay, if you want to define the air gap, you can define the air gap also, or you can just proceed for the next. After that, here you have to give the transformer wound part. Okay, the winding part, if it is the planar or the wound one. So right now it is wound one. Okay, then the number of layers, the number of layer means the number of windings. Okay, so if you have two windings, primary and secondary, just give the two here, so it will create the two windings. Okay, so if you want to specify any layer spacing, then you can specify this also. Bobbin thickness, if you want to specify, and the units are usually here, the mm's are there. Okay, the like the bobbin thickness is there, so 0.1 is the is there. Okay, and then the conductor types are the rectangular or the circular you have. Suppose I have circular one. Okay, so you have to select the conductor type circular, and then the layer properties, and here you have to give the conductor diameter. What is the conductor diameter is there. Okay, suppose I have the conductor diameter is 2.588. So here itself the unit is Okay, in the number of segments I keep as it is 8. Then the number of turns I, for the both primary and secondary, which is 6 I'll give. The insulation thickness I keep it as it is. Then just click on apply. Okay, and then just proceed. Now the winding definition is getting set. Now this is the third one, is the analysis setup. Okay, so you have to select the core material is there, which core material, and here one option you can see here, make full model. Okay, so if you doesn't click this model, okay, if you doesn't click these options, so software will create the symmetrical model, not the full model is there, only the symmetrical model it will create. So if you click on this, it will create the full model, like this is the full model is there. Okay, so it will create the full model, but right now I'll create only the half model is there, or you can see the symmetrical model. So I hope you all know about the symmetrical model. Then the core model 3C94 I'm selecting here. Coil is my copper. I'm keeping the frequency as 100 kilohertz. Okay, here frequency you have to give in the kilohertz, that you can see here, kilohertz. The percentage error, number of persons I will keep as it is. And here the transformer sides, I have to give the transformer sides are 2. Here the primary voltage, if you have, you can give the primary voltage is there. Right now I am keeping as it is 1. Okay, and then I have to define the windings. To define windings, here the layer 1, layer 1, layer 1 side 2, layer 2, layer 2, just click on. Okay, okay, and here after the windings definition, I have to provide the connections. So right now if you have any electrical connection here, okay, suppose layers are connected in series or parallel electrically, okay, not magnetically. Okay, so if the connection is electrically series or parallel, you can just give the series of parallel connections. So right now in this one it is not there. Okay, so I'm just keep as it is. And now the setup is completed here. You can see the analysis setup 3 by 3. The setup is completed here. Now you have to just set up the analysis. Okay, so if I click on setup analysis, it will create the design here, that you can see here. Here you can see it will automatically create the design. It doesn't need to do anything. Okay, this ETK design is there, that you can see. This design is created. Okay, now you can see here, we go for the half model only. Okay, the symmetrical model. If we click on this full model, the full model is generated here. Okay, now the symmetrical model is getting generated here. Now just go to exit wizard and just exit this page right now. Just- and now you can see this ETK2511. This model is created. Okay, the model, you can see the already the design is there, complete design of the max. So what we have to do here, the next part, you just need to go this design, okay, and just simulate this design. Just analyze all, and you can just need to simulate this design, because all the parameters are there, all the parameters you need, all the parameters are given, like the layers are there, the material is assigned. Okay, so here if we have to give the leads wire modification, okay, that we need to give in the material section. Okay, then the excitations, the side 1, side 2. Okay, so it is given the external, the circuit is created here. So this is your side 2, this is your side 1 circuit is there, the resistance is there, and the layer section, the number of conductors is assigned there. Okay, number of conductors is assigned 1 right now. That's why I think the solid is selected here. Yeah, if you are selecting here the solid, okay, then you just need to select the number of conductors as only 1. Okay, because Maxwell consider it as only one object is there, not a number of strands inside the one part. If you if you have the number of strands, then you have to select here the stranded. Then you can just give the number of conductors, whatever it is, 20, 30, whatever it may be. Okay, so we just wait for 1 minute. Okay, so after the completion of results, we will see the completion of the simulations, we will see the results. Okay, so now if anyone have any questions, you can just unmute yourself and you can just ask. Okay, yeah, please free to ask questions. Okay, you can unmute yourself and ask in the middle of the simulations also, not an issue. If you have any software related questions, then you can ask here also.
Good afternoon, sir.
Good afternoon, sir.
Myself Gurdat Gosavi.
Okay.
I want to ask here that the ongoing simulation, that is, please provide a problem statement. The which type of transformer is and which it is used, why chosen these type of parameters. Please explain.
So the parameters, now you need to design parameters are there. Okay, so whatever the parameters I provide now in the ACT extension, these are the parameters I calculated. Okay, so some equations are there. Okay, the basic equations you need to follow to calculate those parameters, like the dimension is there. Okay, how much the winding 1, winding 2 parameters are there, the wire diameter is there, how much the resistance we have to give. These are some theoretical parameters, sir. That theoretical parameters first we have to calculate, then we have to go for the analysis part. So you can say like this is the analysis part, is the second part is there, the first is the design part is there. So you need to refer some
So
equation.
that,
Yes, sir.
yeah. So on these pre-assumptions, so we have made some pre-assumptions. So on
Okay.
that basis, which type of transformer you have chosen? That's was our asking.
Okay, like if you means you are not clear about the which type of parameters we have to design, right?
Yes, and on that basis, which type of transformer we have need to select.
No, sir, it is based on the application, sir. It is basically where you have to use this application, means where you have to use the transformer.
Yes, that's correct. That was why asking where exactly it is implemented or applicable. That's was why asking.
So when you can see, sir, like the power transmission part is there, where you need the higher power transfer. Okay, so in that higher power transfer applications, you have to use the power transformer mostly. Okay, and where you some applications are there when you need a very less power to getting transfer. Okay, or some of the step down transformer are there. So that time mostly for the step down transformer, the electronic transformer you can use, where you need to not transfer that much of power. Okay, like in the power transformers we have to transfer the high amount of power, like the power range for the, so it is based on the power range, sir. Like what is your power range? So if it is in the
Okay.
milliwatt or in the watt sections or the some kilowatt sections, so you can use simply this electronic transformer. Or if your power range is in the megawatt or the kilowatt sections, then you have to go for the power transformer part.
Okay, thank you, sir.
Sir,
Another
how to
parameter.
validate the how to validate the results out of the simulation?
Uh, Sir, the two way is there, sir. Okay. So the one way, if you have the theoretical results, okay. So if you have the theoretical results, we can compare your theoretical results with the simulation results. Okay, that is the one part you can do. Okay, after the simulations, or the other part is there. You have the simulation results. You can compare it with the experimental ones. Okay, so whatever the experimental setup you have, you just need to build the same setup there in the physical setup. Okay, and you have to calculate those parameters, and you can just put your parameters or the do the comparison of those parameters, like what are the output parameters is there. Suppose the flux value is there. Okay, so whenever we are going to design the transformer, we kept one of the flux value in our mind to design the transformer. Okay, so you just need to plot the flux here. Okay, these are the b value is there. Okay, plot the flux here and calculate like how much the flux is there. Okay, it is my flux is the same as I took for the design parameters. Then the leakage inductance is there, the losses are there. You can just compare your results with the simulation parts. So that is the validation case is there. So the two ways there, sir. If you have the theoretical parameters, you can compare it with the theoretical ones also, or you can compare it with the experimental or physical setups.
Okay, sir. Okay.
Yeah. So in the most of the industrial cases, they are just validating the case with the physical results. Okay, because in the assumptions of, or in the theoretical setups or that you can see, we took most of the assumptions only. Okay,
Yeah,
if
right.
we don't have any of the parameters, like we said, this assume x is equal to 2, x is equal to 3, like this. Okay, I'll just give the example. Okay, so in the theoretical setup we assume most of the parameter. So the our results, whatever the results we got from the theoretical ones, is not we can say that much accurate. Okay, as the physical one. Okay, so it is better to compare your results, your simulation results, with the experimental ones. Okay, so you will get the very close match with your simulation results as you compared it with the physical results. So now the simulation is completed here. Okay, now I will show you the results. Okay, so this is the leakage inductance plot is there. Now you can see this is the leakage inductance. Okay, so now it has some formula, like here the frequency we have to given. Okay, I'll show you first design. So this is my side one. Okay, okay, now you can see the side one parameters. Okay, these are the layer ones. I will show you. Now you can see these are my side ones and these are my side two. Is the layer one, or you can see the layer two. Okay, now you can see the this internal are the primary ones you can see, or the this one is the secondary ones. Okay, and this is your core bottom and the core top is there. Okay, in the mesh parameters we gave here the length of the core, the length of the layers are there. Then the analysis setup we have to give here the adaptive frequency is there. Okay, so this is the applications frequency. Like if we solve for the 100 kilohertz or the 200 or the 300 kilohertz, that you have to give here the, or you can just go for the frequency GP and you can simulate for the different frequencies points also, like from 100 to 200 how much points you need, you can just simulate like this also. Here this is simulation is for the 100 kilohertz frequency. Okay. Now this is the leakage inductance plot is there. Now how to calculate this leakage inductance is the question. Okay, so now when you go here, you have this. Now you can see this is the equations. Okay, so you have to plot this equation. Okay, when you go in the output variables, you have the equation is there. Okay, here you have to create the equations by using the inductance parameter. Okay. So like this equation is created, L side 1 side 2 into 1 square. This is basically on the coupling coefficient. Okay. And the results is plot here. And then the same as the loss, core loss is there, solid loss is there. Okay, right now though we are not focusing on the stranded loss because we select the solid here. Okay, we consider our winding as a one solid part. Then the same as the core and solid loss, you can see you can just validate these results like core losses and the solid losses results. If you have the theoretical data also, you will get the better match. So right now you can try with the leads wire technique also. Right now this simulation is not the using the leads wire technique. It is using the solid winding techniques. Okay, okay, the traditional one. But if you have the leads wire, then you can use the leads wire technique also. Okay, and these are just the plots are there. The current density plot you can see. Okay, the ohmic loss. These are the ohmic loss parameters are there. So go here. Let's go to log scale. Now you can see this is the ohmic losses are there. Okay. Then the B plot. This is the B plot. You can see at the core part. B part. If you want to see better, then just okay. This is the core part is there. Then the core loss you can see here also. Okay. So in this way you can see the multiple parts here. Okay. So this is one of the shell type transformer is there. Now I will show you one of the power transformer is there also. Okay, so this is one of the examples of the power transformer that you can see the three limbs are there. This orange is one, you can see this is the LV. Okay, and this red one is like a HV is there. Okay, here itself you can see current one. Here is the HVA, HVB. Okay, HVC are the outer one, and the LV1, LV2 is the this is the inner one. So LV is the inner part and HV is the higher part. Then we give directly the current excitations amp turns, so which is around the amp turns value is around 4 around a 4 lakh ampere current we give here. Okay, 4 lakh ampere current we give here. Okay, for the each phases are there the 0 degree here, and in the next ones the for the B part the 120 and the C part it is a 240-degree phase difference is there. Okay, and then we calculate the results. The results are like profile, convergence part, then the winding part. Losses are there, standard losses. Here we use the standard part and go to matrix sections. The matrix part is also there. Okay. Then the results, impedance boundary, this tank surface losses are there. Okay, so you can calculate the any points here. Like this is the transformer one. This is the tank losses. Okay, the tank surface losses you can see, and this is the clamp losses. At the clamp portion how much the losses are there. Okay, so you can simulate those losses also by calculating some of the parameters are there. And next one of the design and the same design here. So this one is the 3D design, and the same design we have for the 2D one. The same design is for the 2D one. And then we will see one of the transformer part. This is the one planar transformer. Okay, So here the primary section is there. Okay, just a second. Here the primary section is there. Okay, and in the middle the secondary section is there. Okay, upper part primary, and here part 3 coils are primary, 4 coils, and the 2 coils, upper 2 and below 2, it is the primary part, and the middle 2 coils are for the secondary part. So in the secondary they give the load resistance. Okay, so the load resistance they give, which is around 0.4 ohm. Okay, for the secondary part. And for the primary part they give the voltage as the primary voltage, which is 50 volt. Okay. And then they give the materials here. And I will show you now the this leads wire part. Okay, this is the material part. Okay, this leads wire part, suppose. Okay, this is the copper temperature, this is your material, and here you have the composition option. Okay, this means what this material is assigned to the layers part. Okay, the winding part. So composition part solid, you have to select your leads wire, and you have options like wire type, round, square, rectangular. Okay, now the round is there, you have to select the strand number, twisting length factor, you can keep as it is 1 here, and you can give the diameter only. Okay, so if you give the diameter, automatically the leads wire parameter is assigned to those winding or that particular layer part. And then the solution setup is there, the same frequency is there. Here the frequency is around 100 kilohertz, the same frequency is there. And here it is calculating the current versus phase angle. Okay, the primary and the secondary one current, the red one is the primary one, and this one is the secondary ones, that you can see maximum current at this particular 100 kilohertz. In the leakage resistance, and so leakage inductance, and the losses part. Same the fields, the conductivity is there, ohmic loss, copper loss, temperature is also there. Okay, current density plots also you can see. So in this way you can simply do the simulations inside the Maxwell. Okay, so what you need to do the simulation in Excel, you need a simply a CAD model. Okay, now I will show you one of the example, or the sorry, just the overview of any GUI of the this simpler part. Okay, so this is the simpler part. Here you have to do the like like I shown you the example of the flyback converter is here. Okay, so the same flyback converter is built here. Okay, you need to just transfer or import your Maxwell model, add component, and here Maxwell component is there, Simulink component, RMX, IcePack, any component you have for the analysis, the system level analysis. Okay, so you can just add component here. If you have the Maxwell component, you can add the Maxwell electro AC magnetic component here, suppose. Okay, so I will select here. When I click on OK, now you can see. Okay, so this is my planar example. So this my planar is the same design, this planar design. Okay, the same design. Okay, now the same design is getting here. Okay, it is transfer here. You have to create the circuit here. Okay, any converter part, and you have to connect that converter part with the this primary source and the sink part. And here the elements, like I told you, the libraries are there. Okay, so these are the libraries are there, simpler elements, circuit elements are there, passive, all the circuit components, all the electrical components you need, all the electrical components are here, like MOSFETs are there, PWM blocks are there. It doesn't need to create any PWM blocks. Okay, all the PI controller is there, the state blocks are there, the physical domains also there. Okay, like fluidic, magnetic, mechanical part is also there, the mechanical loads parameters are there. So all the load parameters are there. And this is basically the overview of the twin builder. Okay, you can see the twin builder, and here the ROM support: static ROM, dynamic ROM, mechanical, SI wave. These are the ROM support by the twin builder part. So if you have any questions regarding this particular webinar or this particular software simulation, so you can ask here. If anything you want to ask, you can just ask me. Any questions? Any questions you have? To calculate the temperature part, you need to couple it with uh, the ice pack. So after coupling the ice pack, it will show you the temperature part. Okay. Please provide one statement regarding the ongoing simulation. Okay. Inductor you cannot design. Okay. Only the transformer ACT extension is there, not an inductor. So for the inductor, you have to create the CAD design of the inductor, and then you can simulate in the same way in the in the Maxwell part. Okay. So for the inductor, the that ACT extension is not available right now. Okay. Any other questions? Any questions you have? The skin effect loss is there. So the skin effect loss is basically the penetration of your current density. Okay. So if you are providing the AC current, okay, the some loss is there because of the your current is getting penetrated into your conductor. Okay, that winding part, that skin effect, that is also called as a skin effect loss. Okay, because of the your current density is getting penetrated inside the conductor, and because of that the losses are happens. That losses is called as the skin effect losses. So it is based upon the surface, okay, the surface of the conductors.